In the stochastic dominance, the set U contains all possible decision makers. So it means that we only classify X being better than Y in a stochastic dominance if everyone in our group agrees on that choice. However, since we have risk-averse and risk-loving decision makers in the group, it can happen that sometimes you have a risk X and Y, and some people will prefer risk X, while other people will prefer risk Y. However, if the group that prefers Y over X are only the risk-loving decision makers, then maybe you still want to classify X as being better than Y. Why is that? Because you are only focusing on risk-averse decision makers. So therefore, we introduce the stop-loss order. So the stop-loss order will prefer risk X over Y if the expected utility of X, the expected utility of losing X is larger than expected utility of losing Y. And this relation has to hold for all non-decreasing and concave functions. So it means that we only keep the concave utility functions from the set of all possible utility functions. So it means that our set U is now containing all non-decreasing and all concave utility functions. So it means that we are essentially looking at risk preferences of risk-averse decision makers. If there are risk-loving decision makers that have a different choice, that prefer Y over X, I'm not going to take that into account. The stop-loss order is defined using loss random variables. So X smaller than Y in the stop-loss order means that you have to look at the expected utility of U minus X and minus Y. So you subtract the loss X and Y from your initial wealth, which is assumed to be 0. We will now move from losses to income to profit or gains. And we do that in a similar way as we did in the stochastic dominance. We start with a utility function U, and we move from U to a function V, which is defined as minus U of minus X. We know from the stochastic dominance that if U is a non-decreasing function, so U is a utility function, then this function V is again a utility function. However, for the stop-loss order, U is concave. And we will show on the next slide that if U is concave, then the function V is convex. So we will do the proof on the next slide. Let's see what is the implication. So assume that we have stop-loss order. So X is smaller than Y in the stop-loss order. Then we know from the definition that this is equivalent with the following inequality of the expected utilities. You have the expected utility of X and the expected utility of Y. So it means that we prefer to suffer loss X over loss Y, and it has to hold for every utility function U in my set big U, which are now the concave utility functions. If I multiply both sides with minus 1, I get the expectation minus U of minus X. Because I multiply with minus 1, instead of larger, I get smaller equal, and I get the expected utility minus U minus Y. But minus U of minus X, that's exactly the expected utility of Vx. And this has to be smaller than the expected utility of Vy. However, important is that now V is not an element of U anymore, because V, that's what we have here, is now a utility function, but a convex utility function. So what we did is we start with the stop-loss order in terms of loss random variables. So we subtract X, we subtract Y. If we switch to income random variables, my utility function goes from a concave to a convex utility function. So I can say that I prefer to receive Y over receiving X, but it's only for the convex utility function, not for the concave utility functions. So that's why we say that stop-loss order has no interpretation in terms of gains when we look at risk-averse decision makers. If we switch from losses to gains, we switch from risk-averse to risk-loving decision makers. So stop-loss order therefore can only be used for loss random variables. We will see in this, the following stochastic order, which is the secondary stochastic dominance, that is the ordering that you can use for income-random variables when considering risk-averse decision makers. So we start with a function u, which is non-decreasing, and a concave function. It means that the function u looks a bit like this. And for a concave function, we have that if we take, for example, x1 here, x2 here, then we have the following inequality. We define the function v as follows. V is v of x is equal to minus u minus x. So let's then prove that the function v is a convex function. So we start with t vx1 plus 1 minus t vx2, where we have that x1, x2 are like in this plot, and t is in 0, 1. So if I switch from v to u, I get minus t of minus u minus x1 plus 1 minus t of minus u minus x2, which I can write as follows. I put a minus in front and I get this here. Now I can use my concavity because I know that this thing here is always smaller or equal than, which is basically this result here, but then not with x1, x2, but with minus x1 minus x2. So then I get that if this is smaller than this thing, because I have a minus here, my inequality becomes larger or equal than. But this I can write as follows. So here I have a minus. I have minus x1 minus x2. So I get minus u of minus t x1 plus 1 minus t x2. But minus u minus something, that's exactly how we defined the function v. It's v of t x1 plus 1 minus t of x2. So you find that a linear combination of the function values is now larger or equal than the function value of the linear combination. And because it's larger than, it means that v is a convex function. Let's have a look at the name stop-loss order and where it comes from. In order to understand the name stop-loss order, we have to introduce what we call stop-loss insurance or stop-loss reinsurance. So we have the following situation. We have an insurance company, and this insurance company has a total risk that we denote by the random variable x. So x is the combination of all the liabilities the insurance company has sold to its clients. And the insurance company will charge premiums and make estimations of how to determine these premiums in order to be able to repay any future liabilities with a sufficiently high probability. So the insurance company will make sure that it understands what is the average expected loss. So where do you think on average the loss in the future may be? Of course, you know as an insurance company that sometimes the realized loss will be higher or lower. So you make sure that you reserve some extra money in case your loss will be higher than what you expect. So if this happens, meaning if you get a loss that is equal to the expected loss or a little bit higher, the insurance company will be able to repay this liability. The problem is when something really unexpected happens. If you expect a loss of 100 and it turns out that your realized loss is 1000, it's 10 times more than what you expected, right? It's more than you expected, but it's much, much more. And like the cushion you had to absorb any losses that exceed the expectation is still not sufficient to cover this huge loss. So therefore, the insurance company will look for insurance itself. It will say, well, if there is a threshold that we can call K, and as long as my losses stay below that threshold, I'm fine. I can pay any loss myself, but once we breach that threshold, I want to have another insurance company that helps me pay off the losses. So the insurance company prefers to pay a certain premium today in order to swap that risk that your loss will be larger than that threshold K. So it means that the payment the insurer has to pay is the following. If your loss X stays below the threshold K, the reinsurance is not needed and the insurance company will pay the full amount X. In case the loss X exceeds K, right, you had the threshold K but your loss turns out to be larger, in that case the insurance company will only pay K. Any amount that exceeds the K will be paid by your reinsurance company. So it means that the payment of the reinsurance company is 0 when X stays below K. In case X exceeds K, the insurance company will pay K. So it means that for the reinsurance company, there's left the amount X minus K. Because the reinsurance company will only pay if X exceeds K, this X minus K, the payment of the reinsurance company, is always positive. So we denote this thing here. So the amount X minus K, if it is positive and 0 otherwise, we will denote that by X minus K plus. So X minus K plus means it's X minus K if that is positive, it's 0 otherwise. So what is the expected payment of the reinsurer? So what does he expect to pay for this reinsurance contract? It's the expectation of its payoff X minus K plus. And this contract where your reinsurance company will pay any amount that exceeds some threshold K, we call that contract a stop loss reinsurance contract with retention K. And the expectation X minus K plus, the fair premium of this contract, that's what we call the stop loss premium. Another situation where stop loss premiums arise is in option markets. So assume that X, the random variable X, is now not denoting a loss, but is the price of a certain stock at some future moment in time. For example, it's the price of Apple after 1 year. And because today we don't know what the price of Apple will be within 1 year, it's a random variable X. If we think today that this stock will increase in value over the next year, we can buy the stock. We can invest our money in this stock today. If it increases after 1 year, we can sell the stock and we will have a profit. Another thing we can do is we can buy a call option on this stock. So what is a call option? So a call option is a product that if you have a strike K and a maturity big T, in our case the maturity is 1 year, and assume that you take K, the strike, equal to the value of the stock today, then we have the right to buy the stock after 1 year and we pay a price equal to K. So it means that after 1 year we can buy the stock at the price K. And if you take K equal to the current value, it means that if my stock is going up in the next year, I can buy the stock after 1 year at a cheap price because it increased in that year. So what you do with the option, if you are at maturity, then the payoff of that option, so the amount you get, is 0 if your stock ends below that strike price. Because if you end below the strike price, well, there is no need to exercise your right to buy the stock because it's better to just buy the stock in the market. That will be cheaper. If, however, the stock price X exceeds K, then you can buy at K and directly sell at the new price X. What you get as profit is X minus K, which is positive. Again, the payoff of this product is this X minus K plus, the same as we had in the reinsurance example. In this situation, we call the expectation X minus K plus. We do not call it a stop loss premium, but we call it the option price, or at least it has to do with the option price. But you see two very different situations, an insurance, reinsurance situation and an option pricing situation, but these stop loss premiums arise in both situations. Whether you are in option pricing or in reinsurance pricing, in both situations you want to investigate this expectation that we have here, which we call the stop loss premium. So let's have a look. What are the properties of a stop loss premium? First property tells you that this stop loss premium can be expressed as an integral that starts in k over 1 minus the CDF. If you want to prove this result, you use a very similar proof as we had for the expectation of x. So the expectation of x could be expressed as minus an integral over the CDF plus an integral over 1 minus the CDF. That proof is very similar to the proof for this formula. So I'm not going to give you the detailed proof, you can try that yourself. But let's have a look at the interpretation. The CDF here gives you the probability that the random variable x is below small x. So if you then do 1 minus, it gives you the probability that the random variable x exceeds some value x. So it means that we integrate over upper tail probabilities. We are looking at the probability at the distribution of your random variable x from k on all the way to the large values, which is, I hope, reasonable to believe, because in a stop loss reinsurance contract, but also a call option, you are interested in the values that exceed k. What happens below the threshold k is of not a very big importance. What's important there is what's the probability you end up below k, what's the probability you end up above k. And then if you look at the situation above k, there you need the distribution of your outcomes, but not below the threshold k. So in order to calculate the stop loss premium, we have this formula, which is actually the surface between the CDF fx and the constant 1, starting from k all the way to plus infinity. So on the previous slide, you had the formula that expressed the stop loss premium as an integral from k on to plus infinity over 1 minus the CDF. And because we take an integral, you look at a surface, 1 minus the CDF. If you have x here, you have here the CDF fx applied on x, then this distance here from the CDF fx to the constant 1, this length, that's 1 minus the CDF. So if you then take an integral, you are starting in k and you look at this surface here. That's the stop loss premium. And then you see that if your CDF is moving up, coming closer to that horizontal line 1, your stop loss premium is getting smaller. Why is that? Because there is less probability that you take on very large values. If your CDF goes down, then your stop loss premiums will increase because you increase the probability that you get very large outcomes for x. The stop loss transform is defined as the function pi x. So pi x in the value x is a stop loss premium with retention small x. What we do with the stop loss transform, we are looking at not a single stop loss premium, but at the function that expresses the stop loss premium in function of the retention k. Then you can prove that that function pi x is decreasing and convex. What you can also prove is that if you have the function pi x, so if I know any stop loss premium for any x, I can take the right derivative, so pi prime is a derivative, this plus here indicates that we're looking at a right derivative, so that right derivative is equal to the CDF minus 1. So now we have two formulas. We have formula 1 that expresses the stop loss premium, x minus k plus, as an integral from k to plus infinity 1 minus fx of x dx. which also means that pi x of x is equal to, you integrate from x to plus infinity 1 minus the CDF, and now I use dy, right? And then I have a second formula that expresses pi prime x, the right derivative, I do plus 1, I get my CDF. So how can you use formula 1? Assume that you have information, meaning you have data of your random variable x. Then you can use this information to first derive the CDF of that random variable x. So you have all the data, then you get the probability distribution. Once you have the probability distribution, you can determine the stop loss premium for any value x, meaning you can reconstruct the stop loss transform. And that's what you normally do with insurance. If you want to insure a risk, think about the reinsurance with stop loss reinsurance. The reinsurer will ask the insurance company, well, give me information, give me the data of your losses, because we will estimate what are the probabilities for your very extreme losses, where we as a reinsurance company will have to pay. We use that to build a distribution function and then to do the pricing. So you go from distribution function to stop loss premium. However, this second formula here gives you a way to move in the other direction. It gives you a way to back out the distribution function if you already know the stop loss premiums. In an insurance context, this is very unlikely to ever occur because you don't know how an insurance company is pricing its stop loss transforms, right? But in option pricing, think about the call option. If you want to buy an option on Apple with a certain maturity, a certain strike, then you can try to price the option to determine what you're willing to pay, but most likely you will not be able to buy or sell at that price. Why is that? Because you can have a look at the market, you can look at Yahoo Finance or any other platform you're using, and there the platform will tell you this is the price at which Apple stocks with your preferred maturity and strike are traded at this time. So if you talk about call options, there is no need to price a call option because we already know its price. It's on our computer screen. But this expression here, expression 2 here, tells you, well, if I know the prices of my call options, meaning I know the stop loss transform, then I also know the derivative of it, and that gives me a CDF. So for option pricing, this is important because if I look at the market, I see all the option prices which are traded. I can extract the CDF of my underlying stock from these option prices, and I can use the CDF to price more complicated products, right? So we have now two directions. We can start with the CDF and then calculate the stop loss premiums, or we can start from the stop loss premiums and back out the CDF. What is important to see is that the two are equivalent. If you have two random variables x and y and they have the same stop loss premiums, then they have to be the same in distribution, right? So or you pin down the stop loss premium and then the CDF follows from it, or you pin down the CDF and then the stop loss premium follows from that choice of the random variable. We already showed that stop loss order between the random variables x and y is equivalent with saying that the expectation Vx is smaller than the expectation Vy, where the function v is non-decreasing and convex. We derived that result in the beginning of this video. Well then, consider the function Vx, which is x minus k plus for some value k. So you fix the value k and you look at x minus k plus in function of x. Then this function here, if here is k, is always 0. As long as x is below k, the difference is negative, so you get 0. So it's 0, 0, 0, 0. And then from k on, it increases linearly. So then you see that the function v that you draw here, it's non-decreasing and convex. So then you find that x minus y in the stop loss order implies that the expectation x minus k plus is smaller or equal than the expectation y minus k plus for any k. You can prove a stronger result. You can actually also prove that if this relation holds, then that implies stop loss order, right? So what we can show is that stop loss order implies ordering of the stop loss premiums, and you can also prove that if the stop loss premiums are ordered, then you find stop loss order. So this gives you a characterization of the stop loss order. What is important here is that if you have two random variables x and y, you know the distributions of x and y, meaning you can determine the stop loss premiums of x and y. You can compare the stop loss premiums, and that's sufficient to say x is smaller than y in stop loss order, or y is smaller than x in stop loss order, or you cannot classify the risks in the stop loss order. The stop loss premiums, remember, is a measure for the upper tail. So the stop loss order means that the random variable x has smaller upper tails than the random variable y. So the stop loss order looks at the upper tails, and you prefer x over y because x has smaller upper tails. It is less likely to get big losses for x compared to y. However, if you look at the lower tails, then stop loss order does not say anything about the distribution, the organization of the lower tails. This is different from the stochastic dominance. Stochastic dominance means that the upper tails of x are smaller than the upper tails of y, and the lower tails of x are larger than the lower tails of y. Stochastic dominance tells you something about the upper and the lower tails at the same time, while stop loss order is only focusing on the upper tails. Why is that? Because in stochastic dominance, you have risk-averse and risk-loving decision makers at the same time. You have an ordering of your upper tails. X has smaller upper tails than y. That's to please the risk-averse decision makers. You have for stochastic dominance that the lower tail of x is larger than the lower tail of y. That's to please the risk-loving decision makers, because in the lower tail of a loss random variable x, you have the profits. So you have that the risk-averse decision makers mainly look at the upper tail, risk-loving decision makers look at the lower tail. Because stochastic dominance includes both risk-loving, risk-averse decision makers, stochastic dominance will result in an ordering of the upper tails and the lower tails at the same time. Because the stop-loss order is only considering risk-averse decision makers, the stop-loss order will only order the upper tails where the losses are. The last result on stop-loss order that we will consider is the crossing condition for stop-loss order. So this crossing condition gives you a sufficient condition to have stop-loss order between x and y. However, it's not a necessary condition. So there are random variables x and y that are ordered in the stop-loss order but do not follow this crossing condition. So what does the crossing condition tell you? It tells you that if you have a value c and the CDFs of x and y are ordered in one way below the threshold C and the ordering is reversed above the threshold C, meaning that they cross in C, and on top of that you have an ordering of the means, that is sufficient to conclude that x is smaller than y in stop-loss order. So I think it's easier if you see that in a graph. So we have the following. You have a CDF of x, the green line here, that's f of x. You have a crossing point here, and you have a CDF of y, which, first condition, is above the CDF of x below c. So the CDF of y is this one here. It's above fx below c, but once you hit c, then fy is below fx. So this is fy. Alright, if this is the case, then we have stop-loss order. So let's try to prove this result, but before we start with the proof, we call a result from the stochastic dominance, that's that expectation y minus expectation of x. This difference in expectation, I can write this as an integral from minus infinity to plus infinity of fx x minus fy. So the difference between the CDFs of x and y, if I integrate over this difference, I get the difference of the expectations. All right. For the proof, we go in 2 steps. We have to prove stop-loss order, which is equivalent with proving that the stop-loss premiums of x are always smaller than the stop-loss premiums of y. So this inequality of stop-loss premiums has to hold for any k. Okay? What we do is we split k in 2 parts. In the first case, we assume that k is larger than c. That's the easy part of the proof. And then we look at a situation where k is smaller than c. In both situations, I want that the stop-loss premiums of y are larger than the stop-loss premiums of x. Putting these 2 results together proves the result of stop-loss order. All right? So we're looking at this difference in stop-loss premiums. If this difference is positive, it means that y has larger stop-loss premiums than x. I finished the first part of this proof. All right. Now I use the result that a stop-loss premium can be expressed as an integral over 1 minus the CDF. And I can apply this result for y and for x. And then I get the following. I will now put the 2 integrals together into one integration from k to plus infinity, and then I get this result. However, because I assume that k is larger than c, any x that I have here in this integrand is also larger than c, and if I take values x that exceed k, then the CDF of x is always larger than the CDF of y, so this is positive, making this whole integral positive. And we proved that at least for values k exceeding c, the stop-loss premiums of y are larger than the stop-loss premiums of x. Assume now we are in the second situation, where we have that the retention k of our stop-loss premium is below c. Again, we are looking at the difference between stop-loss premiums. And this difference, same as on the previous slide, we can write as an integral from k to plus infinity fxx minus fyx. The problem is that, different from the previous case, this here is now not always positive anymore, because first k is below c, meaning we have x values which are below c, and for these values that difference is negative, and then it switches to a positive difference once I exceed c. However, what I can do is I can add here something extra. So let's have a look. Let's look at k plus infinity. I look at this difference. But now I'm adding something. I'm adding the part from minus infinity to k. However, for this last integral, here I know that this is all negative, right? Because I take values x below c, this is negative, so this whole integral is smaller than 0. So it means that this difference here is larger than what I write here, right? I'm basically subtracting something extra, and that results in inequality. But then I can write this as an integral from minus infinity to plus infinity, fx of x minus fy of x dx. And then remember, from our stochastic dominance, this is equal to the expectation of y minus the expectation of x, which was assumed to be positive. And now I also proved that for retentions K below C, I have an ordering of these stop loss premiums. Combining case 1, case 2 proves that you have stop loss order.